Has settled in my blood, and we don't care about nothing. You giving me that something, giving me. Hi guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. Now let's talk about aqueous equilibria, and in particular buffer solutions. So a buffer is a compound in a solution that resists pH change. And buffers stabilize the pH of a solution by providing a source of protons when a base is added, or a sink for protons when an acid is added. So a really good example of a buffer is blood, where your blood pH is approximately 7.4. So this means if you took in an acid into your body, such as let's say tomato juice, which has a pH value of 4, it's not going to drastically change your pH to pH 4, where that would shut down all your biological systems and it would be really bad. And so weak acids and weak bases act as buffers in equilibrium with their conjugate base or acid. And so as an example, a weak acid HA, which is aqueous plus water, goes to A minus and a hydronium ion. So adding a strong acid to this results in HA formation, and adding a strong base results in A minus formation. So let me write that down for you too. So add strong acid, you get HA formation. If you add a strong base, you get A minus formation. Provided small amounts of strong acid or base are added, the concentration of the H3O plus doesn't change, and this hydronium ion is responsible for the pH value. If you remember, pH is the negative log of this concentration. So when a strong acid or strong base is added in relatively small concentrations, then it basically gets taken up by these individual components of a buffer. The optimum buffering capacity of a weak acid occurs when the concentration of the acid is equal to the conjugate base. So in this case, the optimum buffering capacity in the example that I gave above would be the concentration of the weak acid HA is equal to the concentration of the conjugate base A minus. So let me show you an equation to explain why this is. So remember talking about how Ka, the acid constant, is A minus, H3O plus, which are the products in that equation, over the reactants, HA. Remember, we don't consider water since it's a liquid. And so now, from here, we get the concentration of the hydronium ion to be Ka multiplied by HA over A minus. Oops. My pen is running out. All right, there we go. Okay, and now remember that the negative log of H3O plus is the negative log Ka minus the log of HA over A minus. And so from here, we can rewrite this as pH equals pKa. So you see what I did here. First of all, you rearrange the Ka equation to write it relative to the concentration of the hydronium ion. And then you take the negative log of both sides, the negative log of the hydronium ion concentration, and the negative log of Ka multiplied by the concentration of the weak acid over the conjugate base, and you get the equation pH equals pKa because of these relationships. So, for a weak base, pH is pKa when the concentration of the base is equal to the concentration of the conjugate acid. So we can also write this as POH being equal to pKb. And so these values indicate that the optimum buffering capacity of any system is going to be when the concentration of the acid or the concentration of the base is equal to the conjugate base or the conjugate acid.